Okay, welcome back. This is lesson 7, and the topic of this particular lesson is the heating curve of water. So at this point, we've come full circle because what we're going to focus on now is going to be again the energy of physical changes, the energy involved in physical changes. All right, and the one that we're going to focus on is water. And I have this little schematic at the top of my screen to remind you of what the relationship is between the solid, the liquid, and the gas for any substance. In this case, we're representing water because you can see that we have. I'm going to change the color quick. We have the melting point of water here. So this is melting point. We're going to abbreviate that as MP. And here we have the boiling point of water. So just be aware that other substances are going to have different melting points and boiling points. Why? Because they're different substances. So just remember in the solid of any substance that all of the particles are bonded in close proximity. There's no spaces between them. Solids in general don't flow. And then we have the liquid, which is fairly close in structure to the solid. You've got to eliminate some of the bonds between the particles, and here I'm showing how this happens in general. So once you've eliminated some of the bonding between the particles, now you have clumps, the system can flow, now it's a liquid. And then from the liquid to the gas, we have the separation of all the particles into individual particles. Very quickly, if we were to compare the kinetic energy of each one of these, the kinetic energy of the solid is going to be less than the kinetic energy of the liquid, which is going to be significantly less than the kinetic energy of the gas. So gases have the highest amount of energy. And you know what? That should make perfect sense to you because the particles are completely separated from one another. They're not they're not bonded or in close contact. Now, we're going to be working on the heating curve of water, and what I want to do first is lay down the fundamentals of how this experiment is being done. All right, so imagine that we have a beaker. All right, and in the beaker we're going to put an ice cube that we literally have just removed from the freezer in our kitchen. Now, most freezers are going to maintain a temperature of minus 20 degrees centigrade. And the reason I know this is because I put a thermometer in my freezer just to see what the temperature was. Admittedly, I did this a while ago, but the freezer is going to maintain a temperature of about minus 20. So the ice cube is coming out of the freezer at minus 20 degrees centigrade. And then what we're going to do in this experiment is we're going to heat the substance up. All right, and I'll just, represent this as a hot plate. So what we're going to do is turn the hot plate on. Not only are we going to turn it on, though, we're going to turn it all the way up. So the rate of heating is going to be constant throughout the experiment. And then what we're going to do is take temperature data over time. All right, and we're going to graph it. And what that's going to look like will be this. So we'll end up, we turn on the hot plate, and at the time we turn on the hot plate, this would be time 0. And then we're going to record the data over time. All right, we're going to collect temperature data. And the temperature that we're going to be collecting will be in degrees centigrade. So I'll list that here. And the ice cube comes out of the freezer, so we can establish a time for this. And I'm going to put that here where we start the experiment. This would be minus 20. degrees centigrade, and the horizontal axis here is going to be time. So we're collecting temperature versus time. In the background here, remember, the purpose of the hot plate is to deliver energy. It's delivering thermal energy. Thermal, all right? And thermal energy, as we've already described, you should have a pretty good handle on that, is kinetic energy. So we're delivering kinetic energy to the system, and we're doing it constantly, right? We're never turning the hot plate down, and we're never turning it off. We turn it on at the beginning of the experiment at time 0, and then we're collecting temperature data of the ice. So if you imagine, of the substance here. So if you imagine, I'll draw this over here. We're going to stick a thermometer into this thing. All right, let me label that so it's clear on here. So this is a thermometer. I'll just abbreviate it. Thermometer right here. All right, and you're going to collect the temperature data that way. So this thing is jammed into the ice cube, if you can imagine that. All right, so we're starting at -20 because we pulled the ice cube out of the freezer at the temperature that the freezer maintains the ice. We set it on a hot plate. We turn the hot plate on, and we turn it all the way up, and we don't touch it for the rest of the experiment. So for the entire time frame of this experiment, we are constantly dumping energy into this. Now, here's what the curve is going to look like. So as we collect the data, what we're going to do is we'll see a steep incline here for a while, and then it's going to flatten out. This is supposed to be a straight line. Let me see if I can get that better. All right, so it's a flat line for a while, and then we're going to get another incline for a bit. And then we're going to see another platform. This platform is going to be longer. Again, this is a flat line. There's no slope to it. It's a flat line. Notice I'm saying that a lot. Here's a flat line. Here's a flat line. This line right here, that's not flat. This line right here, that's not flat. And then, to finish the experiment, we're going to have another steep incline. It's about the same steepness as where we started this. All right, and this is what the curve is going to look like for the duration of the experiment. And let me just extend this axis up a little bit. All right, now let's go ahead and define what parts of each of this curve, what they belong to. So in here we have the substance is a solid. Here the substance is a liquid. And here the substance is the gas. Okay, now where you see the line rising steeply, in this area here, as we are dumping energy in, right? Because remember, the hot plate is on, it's turned all the way up for this entire experiment. There's no place in here ever, except at the end where we say, okay, we've got enough data, and we actually turn everything off, right? Up to that point, energy is being dumped into this at a constant level. So in the area here where the curves are steep, your kinetic energy is increasing, and therefore the temperature is rising. This point right here is the point where we reach the melting point of water. So it's 0 degrees centigrade, right? So let me put that in here. This is our melting point. And if you need to, pause the video and think about this. This line is flat. It has no slope. Therefore, the temperature is not changing here. All right? Now, if you notice the next area here, so the line is again rising steeply. So in this area, the kinetic energy is rising. Kinetic energy is going up. So what does that mean? It means that your temperature is rising. All right, and we can do that down here too. So T is rising in this region here. And here T is constant. T is constant. And then notice we hit this next platform where the slope again is flat, where the line is flat, where the temperature is not changing. And at this point, we reach 100 degrees centigrade. And as you should know by now, this is the boiling point of water. And this region, your T is constant. I'll just abbreviate it. All right. Then after a certain time period, you can see that the line indeed starts to rise up steeply again. And in this area then, your kinetic energy is going up. All right, and the T is rising. T is rising here again for the pure gas. All right, now I want to go back and we need to focus on the two areas where the slope is zero. All right, again, what do I mean by the slope is zero? All right, so the line is flat, the temperature is not changing, and we have two places where this is happening. Now, I need you to think about what's going on, because at the beginning of this experiment, we turned the hot plate on and we turned it all the way up. So all the way across both of these flat regions, energy is entering into our system constantly. It's not being turned off. It's not being turned down. So energy is entering the system constantly all the way through here. So why is the slope flat? We see that the temperature is constant across here. So what's happening to the energy that's being dumped into this? Because we see in the other regions where the slope is rising steeply that the temperature is going up in these regions, right? It's increasing from -20 to 0. It's increasing from 0 to 100. And it's increasing from 100 and upwards, right? But then you have these two flat areas where the temperature is not going up, but energy is being dumped into the system. So where is the energy going? All right, I'm going to stop talking for a second and I want you to think about it. Okay, so the energy is being used differently in the two flat areas. Since it's not being used to make the particles move faster, right? The kinetic energy across here is not going up. Then what's happening? So the energy in these two zones are being used to break bonds between water, H2O molecules. And I'm going to abbreviate molecule. All right, both of these regions. So I'm going to take a line here and also direct you over here. So the same thing is going on in both of these regions. All right. Before I diagram what I mean by break bonds between H2O molecules, because I know darn well there's a lot of misconceptions about this right away. We're not blasting apart H2O molecules. We're separating H2O molecules from one another. There's a distinction there. But before we get into that, I want to address the fact that the two horizontal platforms here are different distances. So what is the reason for the difference in the platform length? All right. So let me go ahead and write that down here. So platform length. Platform length. All right. So the melting point takes less energy. Whoops. Takes less energy to melt because fewer bonds need to be broken. To get to the gas, all particles need to be separated. All right, this requires more energy. Right? And that should make sense to you. It takes more energy to get to the gas because you have to separate all the particles that are still more or less bonded up in the liquid, right? And to go from the solid to the liquid, you literally have to break fewer bonds. Now, let me very quickly address what I mean by breaking bonds, right? So to deal with that, I'm going to take and draw a line from here to this point. Now, I want to keep this simple, so I'm going to draw two H2O molecules here. And I'm going to put a circle around them. And this one is bonded to another one. And I'm drawing very simple water molecules. I'm not even putting the external electrons in. Right, so here's the second molecule. And this is the bond. So when we talk about breaking bonds between H2O molecules to go from the solid to the liquid and then from the liquid to the gas, we're talking about breaking this bond here. This is the bond we're breaking. All right, you need to take time to think about this. All right, what we're not doing is breaking up the H2O molecule itself. We're not taking H2O, all right, and turning it into, we're not doing this, all right? So let me just be abundantly clear about this. We're not doing this. We're not. All right, with that, this concludes lesson number 7, and we'll see you soon on the other side.